Okay, people, today we're going to go through something really intense.
Yeah.
And I'm going to show you how you can actually use complex numbers. Yeah. And how you can actually use this thing called phasor diagram. Yeah. I forgot to charge it. That's the problem. Yeah, so I'm going to show you how to use the complex numbers and this method called phasor diagram to solve for the intensity that you have found. What I'm going to do today is absolutely ASP, So don't feel depressed if you won't understand everything in one go. After like seeing it for 10 times, probably you slowly understand it and internalize it. So don't worry too much. So I'm going to start off with a basic idea. The basic idea is this thing called phase difference. I'm not sure whether you are aware of what phase difference is. We went through very briefly, but I just wanted to make sure that you know this. Now you remember let's go from basic first. Remember that when I went through this, that if you have x equals to x naught sine theta, the graph will be a full cycle in 2 pi. But this is quite meaningless if you want to map x against time. We can't possibly write this and expect a time axis to appear suddenly. This is just against theta. So remember that when we go through one oscillation, it is one period. And therefore, we map 2 pi to 1 period. So an arbitrary angle theta, say for example over here, is mapped to time t. So the question is, how do we transform this into a time function? Very simple. All you need to do is to cross multiply 2 pi t equals to t theta. So theta will be equal to 2 pi upon t. So what I'm doing over here effectively is to transform this into a time-based function. You still okay now? Still okay now? Okay, good. So if I want to ask you what's the difference, how far are these two particles apart? X and t. Say for example this and this. In terms of time, this will be, in terms of period, it will be half, 3/4, 1/4, 1/3. It will be 1/4, yes, correct. Now can you see that this particle and this particle, let's call this A and B, this is X and Y. Can you see that these two particles are also t/4 apart? But the time, the absolute time over here, this may be 1 second, this may be 10 seconds. So the time may be different. So if I tell you that two particles are 1 second apart versus two particles are 10 seconds apart, it's not that useful to understand the difference in the state of vibration. So how do we understand this in another way? So we use this thing called the phase difference, which is essentially the thing that we've gotten over here. In this case, it will be 2 pi upon t times t upon 4. It will be pi upon 2. Now, when we say A and B, when we say the separation is pi upon 2, we know that when one reaches the maximum, the other one will be the equilibrium. When one reaches the equilibrium, the other one will be at the maximum position, regardless of the period. So if I tell you that this is 1 second, this is 10 seconds, I don't know what's the state of vibration between the two, because it depends on the period. But if I tell you that these two particles are pi upon 2 out of phase, I know immediately that it looks something like this. Or I tell you that two particles are pi radians out of phase, I know immediately that one is here, the other one is here. And why is it that it is important for us to know this as opposed to this? Because this affects how waves add up together. Now let's take for example, if I got a wave that looks like this, and a wave that looks like this, and another wave that looks like this, another wave that looks like this. Can you see that the time difference between this is different from the time difference between this? This one, I shift this by a smaller time as opposed to this one. This one you need to shift by a bigger time. So if I tell you that this is 1 second apart, this is 10 seconds apart, I have no way of telling how this two is going to add up to become. But once I tell you that these two are pi radians, out of phase, I don't even need to know the time, the period. I know immediately the outcome will be 0. So that's why phase difference is a very important relationship between two waves, as opposed to time difference. Get it? There are a few important points that I brought you through. First point, how do you convert angle to time, or time to angle? Second, I went through with you why is it important for us to even use an angular representation because it tells us the state of vibration between the two objects. And this is independent of time. It is in relation to the period. It is in relation to the wavelength. Okay, because you have to get this so that you understand what is going to come soon, which is the phasor diagram. Now, before we go on to the phasor diagram, I'd like to just give you a question to see whether you understand how to apply this. Okay, so there is actually another formula that looks exactly, almost identical, that is for distance. Let's try one question. Two waves are 20 centimeters apart and their phase difference is pi upon 3. Each particle in the wave undergoes 3 complete oscillations in 2 seconds. Find the speed of the wave.
We'll give it a try.
See whether you can apply this formula and the formula that you have been taught in Sec 4 to find the speed of the wave. That's like the wall scar kind of thing. This is OM2. Now, is the answer 1.8? 1.8 meters per second. 1.8 meters per second. They're like his cheerleader. Wow!
Yes.
Hey, you should copy this example down so that when you go back home, you don't need to rely on that video of Mr. Terrace Chu. Yeah. So that you can immediately understand what is this thing called phase. This is IB. Okay? In like 10 seconds, I'm going to move to ASD.
Oh.
Anyone? Couldn't get 1.8?
I just write 2 pi over t and omega. Is it the same thing? Oh, it's the same thing.
It is the same. It is the same.
Small t over big T equals to 1 over C. So I wonder where that x comes from.
But X is the same. I mean, the same idea. Instead of T, I now change it to X. So same ratio, same method, plus. So the phase difference is actually a very cumbersome concept to understand. Probably let me just allow this neggy person over here to just elaborate further, so that I just want to make sure that you understand this idea of phase. Okay. Imagine that two objects A and B, they're chasing each other. And I shine a light over here, and the shadow over here will be, as this object goes round, these shadows over here will be going up and down. The shadows of A and B. Now, do you agree that if I track the position of the shadow of A, it will actually go like this? Agree? It starts off at the maximum position, then it goes. Now, if I trace the position of this one, it is going to look like this. As the circle goes round, as the object goes round the circle, the shadow position goes up and down like this. Now, you know in your math, what's the phase difference between the sine graph and cosine graph? Pi over 2, exactly. So what's the angle between these two objects?
Pi over 2. Yeah.
So you can actually use this analogy. I think it's quite a nice analogy to have to understand the idea of phase difference. is that when you have two objects when you have two graphs of a phase difference of pi or 2, you literally have two objects at an angle of pi. Now what is interesting about this analogy is that it can also tell you that when A is 90 degrees ahead of B, you can actually say B is 270 degrees ahead of B. Agree or not? It is the same. You shift one by 90 degrees to one side, it is the same as shifting 270 degrees of the other one in the opposite direction. Same thing. Okay. Ready? 5, 4, 3, 2, 1. Okay, let's go.
So,
Yep.
what does a small t represent?
The small t. Where?
Just now.
Just now.
So just now the t time. Time for
Time
what?
for
Time at arbitrary time. The big T represents the period, which is a specific time. Small t is like small x. It's a
so
variable.
represent the time difference between the two particles.
Oh, okay. I see what you okay. In that context, yes, it represents time difference between the two points on the same wave.
Interference again.
Okay, you need to really stay close to with me at this one time. But before the one, anyone cannot get 1.8 in the previous example. Anyone cannot get 1.8. It's okay if you cannot get it. Let me know. don't get stuck with yourself and be happy with being stuck. Oh, okay, then x is really serious.
But one observation is
Same way.
one observation.
Then you get a wavelength as 1
No,
meter.
speed equals to this thing times.
So just wait for a while for it to set up.
Yeah.
Then
Then
we'll
this thing is this. Then this thing you get it. It's somewhere there. It's this thing. This because 2 second 3 oscillations, right? Frequencies is tied together. It's CM. So
Okay. 1.8. Okay. Joseph?
oh sorry. Sorry.
1.8.
Oh, actually.
Okay, I think I better just show in case some of you are still struggling, right?
I use this.
So,
I don't know. I don't understand the formula. I just math.
V equals to F lambda, which is 1.8 meters per second. Okay? So the key, I think, is this part over here. That's the new thing. The rest should be. Oh, I mentioned that the two particles are 0.2 centimeters apart. Also, X is the separation. Wavelength is the wavelength. Yeah. X can be any value. It can be the wavelength, can be any value. But wavelength is specific to it.
Well, it's actually this method is a bit old.
Sorry? I know. I forgot to try. Ran out of battery. I left it
Hertz.
like over 3 days.
Hertz is the Chinese
Like,
version of
yeah.
Hertz.
Okay, let's go. You must stay very close to me because there will be a lot of moments where we Okay, let's go. Now, do you agree that the path difference is this section over here? We went through this before.
Yeah,
This is
sine,
this is the path
cosine,
difference.
cosine.
So this is x, this is 90 minus theta, this is theta, so it's x plus theta, which is the path difference.
Oh yeah, sine theta. Yeah.
Yeah, probably I use theta so that it's less misleading. Because in the very short form, I need to use x. Now, do you agree that this is your x, which is the distance between these two trains of wave?
Yeah.
That means the two waves are offset by a distance of x. Yeah, that's what we mentioned. So the phase difference is actually 2 pi upon lambda d sine theta. This is your phase difference,
Yeah.
which is what we did
Makes
just now.
sense.
Still here?
No.
This is the method. This is what we call phasor diagram method. How do you represent these two waves at the phase angle of this? We use this. This is amplitude of source 1. This is amplitude of source 2.
Vector.
And you're offset by the angle of.
Okay, get it.
So we represent the amplitudes of the two waves by this diagram. That means they are the same. Let's say it is A naught. This is A naught. The magnitude is A naught. And we represent this of this situation by this angle. So the resultant amplitude is the vector sum of these two. This is your A resultant. Okay, this is the method. Now, this, if you do the math, it is equals to 2a naught cos phi upon 2. Now why? Can you see that this angle plus this angle will be equal to this angle?
Yes.
Single, remember? And these two must be the same angle because it is isosceles.
Why isosceles?
Because this amplitude is the same as this amplitude.
Is it the same? You give it as the same, sir?
Hmm?
You add up two waves of the same amplitude?
Amplitude, yeah. I say A naught, A naught. Yeah, so it is isosceles. So this angle over here, let's call it alpha, will be the same as this alpha. So 2 alpha equals to phi, so alpha equals to phi upon 2. Now, which means the amplitude resultant is equals to 2a naught cos phi upon 2, which means the intensity, which is proportional to AR squared, is proportional to 4a naught squared cos squared phi upon 2. Which means that I is equals to 4 times the intensity of each of them, cosine squared 2 pi upon lambda d sine theta.
Yes.
Whoa, whoa! Now, if you use a graphics calculator to plot I against theta, this is exactly what you're going to get. Which is a double slit interference method. Which is a double slit interference method. If this theta over here is what you plot against. If you plot the resultant intensity against the angle at which you are sweeping across, this is the graph you will get if you use a graphics calculator or Wolfram or whatever.
But sir, I thought 4 times I naught cosine square something is a constant.
No, you're changing this.
Oh, it's inside the cosine square.
Yes, correct.
Oh, then sir, shouldn't you like the part it touches the theta axis be sort of sharp?
So again, the point means
But it's cosine square, right?
yeah, cosine square of theta. I mean cosine square of this times sine theta. It's cosine square of sine theta.
Oh.
Yeah, it's not cosine square of theta, it's cosine square of sine theta.
Okay.
Okay?
Explains the
So this method is a very powerful method, but there is one problem. What if I have 5 sources? If you have 5 sources, the thing will get really messy. It will be like this, like this, like this, like this, like this. Then you just have to add. So it gets progressively more and more complicated as you add more and more sources. So what I'm going to show you is another method. But before I show you another method, can I just give you 30 seconds to be absorbed?
So how do you get A equals to 2A?
Okay, let me draw a bigger diagram so that you can see it. Do you agree that this is theta upon 2 or phi upon 2?
Yes, please.
Now, if I split this up into 2, do you agree that this is A naught? This is A naught cosine phi upon 2. It is the same on this side, right? So it's 2A naught cosine phi upon 2. Okay? Okay, cool. This will not come out in IB, confirm same job, but it can come out in your ASP.
So what do we use this for?
Sorry? You will, okay. If you want to understand things, there will be certain situations where I just have to ask you to accept it. Then you will just have to accept it if it is IB. There are certain things where you just have to accept it because the derivation, I just tell you that there's a physics behind, there's a math behind. Now this is what I'm going to show you, the math behind certain things that you have to accept if you stop at IB level.
So what is the pass rate of the AST paper?
Rather high. Usually the pass is about 80%.
The distinction?
Distinction is the
Decisions
problem. Distinction is the problem. I realize that whenever I realize that it's almost like a biological system. You know, biological system, if your body temperature goes to like 39 degrees, just like 1-2 degrees, everything, all the cells will die down. I realize that when I said that slightly more, there we go. To my bones, the distinction rate just went down to 1%. And when I said it in a very reasonable way, usually the distinction is like almost 1/3, half a block.
So is the passing still like?
So whenever I adjust it a little bit only, the distinction.
Is the passing still like 40%?
Yeah, 40-70%. The two boundaries. Yeah, 2 boundaries.
So I can
No worries.
random
If you listen attentively, you will not fail.
Not
You
fail.
will not fail unless you want to prove me wrong. You sure? You sure? I prove you wrong. Okay. Coming back to this, okay now. Okay, yeah. Okay. The next method I'm going to show you is to do with complex numbers. Cool? Okay. I represent an oscillation using this notation. In complex numbers, you know that ei omega t is sine, cosine cosine omega t plus I sine omega t. Yeah? So I just use this to represent the oscillating function. Then the x, the source 2 will be x naught ei omega t plus phi, which is the phase difference between the two sources. Still okay? Yeah. Now then x resultant is just x1 plus x2, which is x naught ei omega t 1 plus ei phi. Still okay? I just add this two. You like? Okay, this is the part where I really a little bit of math to do. Still okay? It's simple math. It's really math.
Yeah, makes
So
sense.
yeah. Now, do you recognize this thing or not? Conjugates, exactly. If you have eix, it is actually cosine x plus I sine x, right? Eix is equals to cosine x, 2 cosine x minus I sine x.
Yeah.
You add the two together, eix plus e minus ix equals 2 cosine x. So this will be this.
Yeah, makes sense.
So this, can you
Makes
see
perfect
that?
sense. Yeah.
Which is equals to? Now, do you see the similarity between this and this? And this is the amplitude. This is the amplitude of the oscillation. So just to square this, you get the same equation as before. Two different methods, same conclusion. People were more visual, were more shape. Yeah, visual people would just like to bulldoze manual now. But trust me, if you get like 5 sources, 10 sources, infinite number of sources, this one 2 sources still okay. I give it 10 sources, that's it really. You were like, then how do you get that thing? Right? Yes?
No. I just don't get the math at all.
Okay, we should get
The second to the third step.
Yeah.
1, 2, 3, 4, 5.
Fourth
Fourth
second.
to fifth.
4th to 5th. Okay, 4th to 5th. On 4th to 5th, what I did was I factorized another e to the power of I phi upon 2. You see, this is the one that I brought up. Additional one, because this didn't have this portion. If you multiply e I phi upon 2 into here, can you see that this will be 1?
Yeah.
And if you multiply this into here, can you see that it's this one? So what I did was just a math trick. I needed this thing to come out. So that's why I brought out half I phi upon 2. Okay? Later on, when we go to single slit diffraction, I'll revisit this method and I'll show you how I can split this up into infinite number of slits. And then I'll show you how to do that beautifully. I think it's gonna be. Okay?
Still trying to grasp on that.
I mean, the video is not taking hours. Just the voice will not be as good today. Okay, now I'm going to show you using this method how do you derive simple harmonic function. And I'm going to show you how you include damping forces inside simple harmonic. Okay, very simple idea. Air resistance depends on speed, displacement, or acceleration. In the case. Speed, exactly. So if I got something that's oscillating like this, do you agree that if I pull an object distance x, the restoring force will be kx? If I pull it by x, the restoring force will be negative direction and will be proportional to x. So ma is equals to minus kx, and I have to add another function alpha v, which is the air resistance. Why minus? Because air resistance always opposes velocity. The only additional component is this part. Okay?
sir, what?
But if it's opposing the restoring motion, isn't it positive?
Opposing the restoring motion. So what it does over here is force air resistance is equal to minus alpha V. It is minus of V. It is not minus of x. It's minus of V.
Oh.
Yeah, air resistance. It always opposes motion. It doesn't opposes displacement.
Okay, moment.
What is the direction?
Of the air resistance.
No, the resulting.
Oh, resultant force, it depends on the relative magnitude of this. Because this can be a positive value depending on the velocity. If the velocity is in the negative v direction, then this can be a positive. It depends on the relative magnitude. So just did it as well. This is the part. Okay. I just shifted everything to one side.
Close to 0.
No, relax.
What else can it be?
Okay. This is just dx. This is just dx dt. This is x. This is d of this, the differential of this. So it's as well as d2 x dt squared. It is actually dv dt. You okay? Yeah. Let x be equals to x naught e to the power of I. Oscillation, right? Oscillation, yeah, oscillation. Now this is the magic, huh? I don't know whether it's making things simpler if I divide everything by m. So d2x dt squared, I'm going to call this plus a dx dt plus b x dt. Still okay? All I did was to represent alpha upon m by a. Simplify the thing a little bit. Cool. Now, if I differentiate, let's start from this side. Can you see that this is b x naught e I omega t? Still okay? Plus a I omega. Still okay? I differentiate exponential. I bring I omega t out. I omega out. Okay, then plus. Yes, right. I differentiate again. Okay. I bring I omega twice. Now, beautifully, I can cancel this. I divide 12 by x naught I omega e I omega. So what I have over here is minus omega squared plus a I omega plus b equals to 0. Now I have a quadratic equation relating omega a and b.
But there's a I.
Yeah, it's okay. Just leave it as that. So to simplify, I think it is simplifying. I'm not sure whether you think it's simplifying, but just make omega squared. I personally prefer omega squared to be positive. So therefore, omega is equals to minus of minus IA plus minus square root of b squared, which is going to be minus a squared plus 4b.
Yeah, makes sense.
B squared minus 4ac. Still follow? Okay? Okay. Now let's take a look at what's the physical meaning. That's more important. Now if I plug omega back in, okay, probably let's simplify it. This will be a plus minus square root of 4b minus a squared upon 2. Now if I plug this back in, it will be x equals to x naught.
It should be IA, right?
I.
Oh yes, I yes, correct. Now if I plug this back in, this will be, let's take for example the one where it is plus. So it will be EI T AI upon 2 plus square root 4b minus e. The upon 2 probably I'll just take this in. Now, let's understand what this means, okay? Can you see that this is an exponential decrease with time? It
Yes.
decreases with time. There is no I inside there. Now, what does it mean? It's just an exponential decrease. Now, this has an I over here. Now, what does it mean? Whenever you have I omega t, it means that it is actually an oscillatory function. So, combined together, what this means is that this object over here is going to go through
Wow.
Make sense? Absolutely.
Wait,
That's resistive force.
wow.
Yeah.
Wow.
Okay. This one is an exponential decrease. There's no I inside here, that's why it is not an oscillatory function, it is just an exponential decrease of what? Of your x naught. It is an exponential decrease of your x naught. So the x naught starts to drop, the amplitude starts to fall exponentially. This has an I inside here, so it is an oscillation function. So you take oscillation function, multiply by this, you get an oscillation where the amplitude decreases. Next. Let's take a look at what happens. This is when b minus a squared upon 4 is bigger than 0. Now what does it mean? It means that if you look back, this is actually your b, right? This is your a. Now what does it mean when I say that b minus a squared upon 4 is bigger than 0? It means that the spring is very strong compared to the air resistance. This is strong compared to this. So there is still oscillation. Now what happens when this becomes stronger and stronger?
I cancel out e the power of negative something.
When this gets stronger and stronger, what happens is you get the condition where b minus a squared upon 4 equals 0. Possible? Yes, absolutely possible. Say for example if you're oscillating in water, or if you're oscillating in chocolate syrup. Now what happens when this is 0? Can you see that this whole term over here goes away? And all you have is just no oscillation at all. It just behaves. So in a pendulum concept, in pendulum term, you stretch it one side, stop. This is what we call light damping. This is what we call critical damping. There's another one which is called heavy damping, which I'm not going to go through. Because it's a little bit difficult. Because all of you, your face looks like you're already very shaken. Very shaken. Okay, let's rewind all the way back. I think all of you still okay then. Got nuked. Got brain nuked.
There is the opposite, he only gets the middle part.
Okay. So the middle part basically is solving it, is applying this part over here, solving it. But I think the most critical part is when you plug it back into here. What's the physical meaning? There is a point that makes sense. But you need to take a take a look carefully over here. Take carefully over here. This is b minus a squared upon 4. If you plug everything back, it's actually square root of k upon m minus alpha squared upon 4n. Now what does it mean? You see, very interesting. If you look into IB formula booklet, whenever you have string attached to a mesh, the omega is always given by that. But when you have a resistive force, can you see the omega is now smaller? Now which means that if you oscillate something in air, or if you oscillate something with a resistive force, the natural frequency is actually lower. Does it make sense? Absolutely. You oscillate in air, obviously there's some resistive force, so the oscillation frequency is lower. Okay? Are you trying to like understand it now, or the lack of activity on the desk? Will you be tested? Let me repeat this again. Will you be tested in IB? No, absolutely no. Yeah. It's 40 minutes, so I thought I would just blast you away. So the 1 hour, 40 minutes you can do something more satisfying and encouraging. Cool. People, I think it's time already. I will revisit this method again when we do single slit diffraction method in topic. I'll show you how powerful this method is.
So like this question we can't do it, right?
Single slit cannot do.
Oh, okay.
Single slit cannot do. I'll show you how. It will come in topic 9 on 2.
Oh.
Yeah. Cool, Ken? Thanks for your day, and thank you. You look really enthusiastic. Traumatized.